Yeah. It's a great pleasure for me to be here. I'm from JD.com, Business Growth Unit, and I'm representing our team to present our work. Like the host just mentioned, the work is optimizing gross merchandise volume via DNN-MAB and ranking. Okay, so maybe some of you do not know JD.com is one of the largest e-commerce in China, and of course another one is the host out here. And every day we have like 258 million daily active users who come to our platform, and we have 557. This is regarding our Q2 earning release. Million US dollar daily revenue, daily GMV actually generated in our JD's platform. And we process billions of requests every day and tens of millions of orders every day. And we have tens of different use cases for our recommender system use cases. And here you can see there's different layouts. Say you can see this is ranking for different apps for mobile app, and this is how our app looks like. And for some of friends not familiar with our app, I have a little demo to show you how it's going to look like. And you can see here, actually, we have different use cases. And you see this is our front page. You open up the app, and you see several different sections. And this work actually is mainly focusing about our waterfall streaming recommendations. And you can see I'm manipulating my app and goes down and down and down. And then I see several different things. Actually, this is what I'm doing browsing every day. So I'm interested in a deep learning book and taking to look at it, and then I go out. And of course, I'm interested in some other things. I can do different things on this platform, basically. I can place orders, I can have the item details, it's really convenient. And for this, you can see, actually, for the fact, we have each user come to our platform, we retrieve hundreds up to 1,000 items to the user. We cannot show all of them. We have to pick out the most relevant items we think the user potentially would like to buy. And so, but then basically it's that the quality of our recommendation becomes the most critical problem. The more accurate, the more precise we do, the more revenue we get, the more successful we can make. Okay. And let's say how we implemented this in the backend. So when the user comes to our platform, say we already retrieved several hundreds of items, and users, like you see, they trigger the water stream recommendation, and for each time they make a request, we retrieve 20 items to the user. And we monitor the user's actions, and the user may click, browsing, making orders, and then we use this feedback information to retrieve another 20, and this procedure goes on and so on. And let's look at this problem in, say, system design perspective. And our user comes in, and our recommender system talks to different databases, talks to, for example, user database, item database, and also some other content database. And we processing this kind of information and retrieve those items we think that most relevant to the user. We pass through the post retrieval module, and then pass to our online ranker, which is learning to rank DNN item ranker. I will introduce in more detail later on. And one may ask, what's the functionality for post retrieval module? Basically, there are some items we think are not appropriate to show to the user. For example, some items may contain some redundancies. Some items user already explicitly express they're not interested, they dislike it, and some other items user may already bought it. Or some other items that item may contain some sensitive information is not appropriate to show to the user. Okay, so far so good. So I already introduced to all of you that we have systematic way to recommend to different items to the user, but unfortunately there's some flaws we would like to fix. So that's why we have this work. So first, our ranking contains some redundancies. For example, like some of the graduate students interested in some book, and our recommender system will retrieve a lot of books that think, okay, graduate student may be interested in, and demonstrate to the user, but actually they contain some redundancy. Redundancy, for example, book 1 or book 2 may be really similar to each other. Maybe it's better for us to just show one instead of 2 books to the user. And like another case is users' real-time intention varies over time. For example, when you come into the app, maybe you just want to buy a skirt, and later on you think, okay, this yogurt looks good. I want to buy some food. So how to catch up this real-time signal and reflect the signal to a ranking is a critical problem. Another one is, say, well, similar to the second one, actually, since our rankings is mostly decided beforehand, so it's really hard for us to capture those variation of user intention and change the rankings dynamically. Okay, so our team smart folks think of idea, say we plug in another post ranker, which is MAB, that's very similar for the first talker. Actually, it's a reinforcement learning perspective. And we use this MAB post ranker to dynamically learn the user's online intention, which include click, impression, conversion, is different kind of signal. And use this kind of signal to adjust our ranking and change our ranking so our result could be optimized. So here, let's first take a greater detail for DNN per ranker. Actually, our DNN per ranker, it's a pairwise model design. It's pretty in upset form. Actually, you can see we have two mirror 5-layer DNN. Actually, there are 1 input layer, 1 output layer, and 3 fully connected layers. And their parameters are mirrored. Basically, it means they share the same parameters. And when we generate the training data, we generate a pair of training data that comes from the item, the user, and other content features. And this pair of items is one of positive samples, one of negative samples. Positive sample means the user explicitly shows some interest. They may click onto it, they may place an order. Basically, they show interest on this positive sample. Negative sample means we expose this sample to the user. Maybe some food, maybe some other stuff, SKUs, and the user ignore it. It means the user is not interested in it. So basically, we'll pass through this model and let the model do the classification. And then in the end, when the model did a good job, we take one part of it and put into our DNN per ranker, say to do the pre-ranking. So let's look at the loss functions. Actually, if we look at it in the greater detail of this loss function, you can find, just like I described, Y are our classification, T are the labels. Actually, basically it's that we are not only want this classification to do a directionally correct results, but we want those positive samples are separated as wider as possible by our classifier. And the M is basically the tuning parameters, which in our experience basically range from 0.6 to 0.8. And you can understand this and sort of represent the margins of this classifier. And lambda is actually GMV related tuning parameter for our object function. Basically, what it means is some SKU are more important than others. For example, you want to buy some yogurt, but if you buy an iPhone, I will make more money compared to you if you buy a yogurt, right? Okay, so like I mentioned before, we have a MAB post ranker to help us do a dynamic ranking. So here's how. So basically, a user comes in our platform, they retrieve several hundreds of items, and for some of those, they express interest for example, they click onto those items, place orders onto those items, and some other SKUs are not interested, they just ignore it. And we categorize different items based on their categories and formulate them as arms. And for those items the user interested, we basically want to learn the distribution, the beta distribution, and want the beta distribution to simulate this result to give larger probability. So basically, if we have a larger probability to show this item, the user have more probability to click onto those items. And on the other hand, of course, we de-emphasize those items that the beta distribution have smaller probabilities. So, like I said before, I may be this model embedded could help us, but some may ask why a revised MAB, why the normal MAB? So the truth is actually every user comes to our platform. I'm not sure about Taobao or Alibaba, but Tmall, maybe the female users spend more times. But in our experience, like for users come to JD, they usually browse less than 10 pages, which corresponding to up to say 200 SKUs, no more than that. If you use a normal MAB, you will have a lot of iteration to learn the parameters, which is really a waste, and we cannot afford it. Once you learn parameters well, and the user gone, you gain nothing. So we need a revised one to delicately help us to set up those parameters, and based on those carefully set up initialization, we update those parameters by the user behavior and fine-tune this parameter to help us. So before we go to the real system, let's talk about the case study. Let's prove our assumption I mentioned earlier, say why we need a revised MAB. So here we have 5 different methods, and I will say 3 of those are state-of-the-art MAB, actually. Sorry, three of those are the state-of-the-art reinforcement learning. One is from Grady, one is UCB, and one is just normal Thompson sampling. And our method is revised Thompson sampling with specially designed initialization. And of course, there's a naive baseline, which is the random selection. So here, we simulate 5 arms representing 5 categories. And each category is totally decided by a pre-designed hidden distribution. And for each round, we just randomly generate probability from the 5 arms. And we select the largest probability as a winner to show as the item. And each category has a threshold probability that represents the user's interest in toward those categories. If the item is greater than the threshold probability, that means the user is interested in this item. If not, the user just ignore it. So basically, the item fails the user's current intention, and basically means that the item is not the optimized one for the current recommendation. And for the rewards, we define, for the sake of simplicity, we define 1 if the user click onto those items, and 0 if the user ignore. So here our goal is to learn how fast and how good each method for learning those users' online behavior. And here are different plots. Upper one are the gains, and lower one are the regrets. And the right side ones are just a zoom in for the left side one. And if you look at the figure carefully, you will see that the UCB are slightly better compared to the normal Thompson sampling, which is as we expected. And actually, this part is just a zoom in, like mentioned, of rectangle area. And our revised Thompson sampling is quicker compared to the 2 methods I just mentioned. And in the end, these 3 methods merged into one line. Basically, which said, in the end, for the bound perspective, these 3 methods are relatively similar, performance. But regarding the speed, our method is much faster compared to the others. And the regret shows similar information. Actually, our methods keeps the lowest. So here, let's look at the implementation algorithm. Say, when the user comes to the system, say, we already have the historical user behavior log for us to learn the relevant SKUs for the user. And we use those information to initialize our different arms to set up those beta distribution parameters. And when each round user shows some interest towards some items or ignore some other items, we update those parameters by updating the alpha and beta and justify the scores after we update the alpha and beta. And then for the next round, we use this updated parameter to generate new distributions and generate new probabilities to recommend new items, so we can check the optimized ranking and the revised ranking, what will cause the user's change of online behavior. Okay, so here, since we're talking about real money, let's test this method to our implementation, to our production system. Say, for GD, we have different, say, 10 different buckets. We call it small buckets, 10 different buckets. And each of buckets contains 8% of total traffic. And for the remaining 20, serve as a control bucket. For some of you already very familiar with this online bucket scheme, and it's pretty standard. And we put this methods into one bucket and test over the rest. So there are some real other methods for us in the implementation comparison. One is DNN-RT-active, basically it's DNN with real-time feature incorporated. And another one is DNN-MAB, which is OR method. The other one is DNN plus normal Thompson. We want to verify again whether or not OR assumption really works in the real time system, or it's just OR guess. And like I mentioned, we're talking about the revenue, we're talking about the money here. We're looking at the DCG, which is a pretty standard of least-wise metric for different methods. And since in our waterfall recommendation scheme, we have a concept of page, we want to also look at a page-wise performance of DCG regarding GMP. And here, like this identifier function, basically 1 means the order, like user make an order toward a certain item. 0 means the user does not like the item somehow. So basically, only if the user makes some orders towards some items, we take this into account for DCG computation. Okay, so here is a comparison for our methods compared with DNN with real-time features. You can see there are 2 curves. Say, at the very beginning, these 2 curves perform very, very similar. Say, because by the description of this algorithm, there's no difference for the ranking for the items they see at the first page when the user comes to the system. So this is really straightforward. The user sees the same item, so that's why there is a similar performance. And when the page, the first couple pages, the gap becomes wider and wider. Basically means or MAB ranker successfully learn the user behavior, justify the ranking. The users buy the better items. The user have a better rate of convergence and or performance get better. And the interesting is that when the page number goes higher and higher, the performance gradually merging to the same line again. Similar like what we see in the case study. Like here, when the page number goes higher and higher, the DNN real-time feature methods catch up the real-time user behavior and show the right item to the user. But I would say, okay, this is sort of too late compared with the OR method. And here, basically, this is just a percentage bar explaining the same thing compared to the upper graph. Okay, so here last 2 pages are also the performance comparison between OR methods and the DNN and the real-time, and the DNN plus normal Thompson. Like I mentioned before, let's first simply jump to the summary. You can see that if we do not have the careful initialization, the Thompson simply won't help. The Thompson will even ruin your whole system. Your performance will get worse instead of better. But with some delicate, careful initialization, or Thompson works. And the GMV got greatly boosted, and or other metrics got boosted too. So basically, this is also another comparison between the daily-wise DCG and page-wise DCG for DNN-MAB and DNN real-time features. You can see that for both of these metrics, or DNN-MAB beat the DNN real-time features. Basically, which said by adding this MAB post-ranker or system in general will boost the performance a lot. To wrap up, say in this talk, I introduced a dynamic ranking framework. I hope my audience will learn something from this. And say we combine this deep learning DNN and MAB post-ranker together, we can have a better performance. And we also adopt, regarding with MAB, we adopt the revised Thompson sampling, like I mentioned before, which will incorporate with DNN pre-renderer, we can have the performance boost. And regarding with future direction, we plan to introduce other reinforcement learning framework. So when we talk about reinforcement learning, of course, there are not only the multi-abundant, there are a lot of others. We want to try them out. And also, inside our company, currently we're not only looking at our revenue, not only looking at our GMV, but also the user experience. There will be some other metric, for example, the clicks, the time span, and other user experience we want to optimize at the same time. So how to optimize multiple objective functions is a really interesting task in front of us. So this is two directions we want to try our efforts in the future. And I guess this is relatively about my work. And thank you for listening.
Really interesting talk. Thank you. So the ranking version of comparing two items is very interesting. I was wondering in terms of modeling an item itself, is your approach different from what's known as contextual bandits? I don't know.
Contextual bandit.
So is the intuition the same?
Well, we are inspired by the contextual bandit. And I think that the main difference is that we incorporate this bandit problem with a deep learning framework we designed inside of the system. And basically, you can think of this as sort of a revised version of contextual bandit, right? So, yeah, but yes, I agree. Like, this works is not totally like from zero. We designed a new bandit algorithms, not like that. So basically, for like I mentioned before, for a bandit to work successfully inside the system, you need some careful designs. For example, the DNN model has some scores. How do you use those scores, and how you incorporate the scores towards your distribution? So make it work. Like, of course, you can introduce other versions of contextual bandit inside, for example, like the DNN plus the normal Thompson, or DNN plus another version of the contextual bandit, but not sure about the performance. So in order to make it work well, you need some tasks. And that some of those tasks may be dirty tasks, some of those may be some careful design tasks, I'm not sure. But yes, I agree, like this is inspired by contextual bandit.
Thank you. I have a follow-up question. So this is a general question about experimentation. It's very impressive that you can hold down the whole website for 7 days and do A/B testing.
That's right.
Or 10 bucket testing. Is there any other sort of A/B testing going on at the same time that you have to consider?
Great question. Great question. Yes. So basically, different companies have different schemes for A/B testing to make, say, your experiment results statistical, meaningful, convincing, make your testing result not let's say, polluted by other experiments. Say in the word algorithm, say that's why we have control bucket there. So basically, control bucket do not have any experiment going on that bucket. I want to compare with a small bucket, say towards a control bucket. How proportionally this bucket comparing with the control bucket. And once you prove your algorithm works, we make it to the whole buckets. And we also have a holdback. Holdback means, say, you still need to monitor your algorithm is meaningful if you put sometimes some algorithm works in the small bucket, but not for the whole bucket, for all the traffic. But you still need to make sure your algorithm works for the whole traffic, and so that's why you have a holdback. For the whole traffic, you implement your algorithm first, have a small bucket, and you promote it to the whole buckets compared to the holdback. But if both procedure prove your algorithm works, you have successful experiments. Yeah.
Thank you.
It's very interesting. You mentioned MAB use algorithm real-time feature. Yeah. Did you try if we train our DNN real-time with real-time feature? What worked with that?
Okay, so I think you were talking about, maybe it's my fault I didn't describe crystal clear enough, I think you're talking about DNN with real-time feature.
Yeah.
Yes.
With real-time feature, it is capable. Another capable if we train real-time. We change our DNN parameter real-time.
We change our DNN parameter real-time?
Yes.
Okay, yes, that's a good suggestion, yes. So basically, my understanding is currently our system is not designed that way, but I'm not arguing we cannot do. It's just because, of course, you can do some different design for the online ranking. One is like you mentioned, like I think this is sort of similar to the tree base, for example. You have different parameters, and when user online behavior change, you have different parameter triggered, and your DNN parameter will change. Another one is, say, it's like how you design the leaf, right? Say you fix the DNN for the root node, and for different user behavior, you trigger different paths, different parameter goes on, or you fix this whole DNN model and say how like we described here, have another ranking block to do this job.
Yes.
My understanding is this is just different paths to reach the same goal, to augment the ranking, right? But I agree that one way is like you mentioned, to have different parameter laying on there that triggered by different user online behavior, right? But I would say compare with model complexity. For example, let's say this one we have small number of model parameters. This one is really lightweight. And I'm not saying your way is bad, but your way is, I would say it's more complex, right? Say you have a tree base, for example, you have one DNN parameters, another DNN parameters, and there's different behavior, you figure further details, so this tree will become huge. And this parameter will become, well, depending on how detailed, how fine-tuned you want your model to perform. And it may perform better, it may perform not as good, but I would say compared with model complexity, our method is lightweighter compared to yours, right? But I agree your suggestion is good. Yeah.
Yeah, because I have to do some scenario experiment on this. I found if we train real-time plus real-time feature, it can get scenario result.
That's right. And maybe we can talk this offline. And we also have some question in our team, say how you figure, say basically the question is more engineering perspective, how you figure the latency, for example. Let's say, I think you will have different conditions to trigger different parameters. And the user have different online actions. For this one, it's just updating those parameters. I don't need to make judgment. But for your case, let's say, if a user do something and one set of parameter trigger, potentially there is some latency we need to figure out. Right? But I would like to discuss